In this lecture, I will discuss about the storage elements which will be used in sequential circuits, right? So these are the two types, that is latch and flip-flop. So we'll see in this lecture only what are the different types of latches and how to design these latches. So generally we'll have two types of latches, that is SR latch and D-Latch. So you can implement the other latches like JK latch or T latch also, but generally we'll discuss about SR latch and D latch. So in the flip-flops we have to go for SR, JK, D and T flip-flops, right? So you'll see the functional tables, characteristics table and the excitation tables of all these flip-flops, right? Now in this lecture we'll discuss about this SR and D latch. Now we will define the storage element. So a storage element in a digital circuit can maintain a binary state, that is either 0 or 1, indefinitely as long as power is delivered to the circuit until directed by an input signal to switch the state, right? So unless until we give as an input to change the state, it will maintain that binary state only, either 0 or 1, right? So that is a storage element. Now to design these storage elements for this digital circuit, always we have to use the gates only, right? So where this all started is, suppose think like this, a inverter is there, right? And this inverter output is connected to one more inverter. This output is connected to back to this inverter. Now think that suppose if I give a 0 here, what is the inverter output? I will get 1, not gate. Then this 1 is going to this inverter. So what is this? I will get 0 only. That means this is 1. So it is storing 1 indefinitely as long as we give the power to this inverter. Remember, this is not a simple triangular box with a bubble. So inside this, transistors will be there. To work those transistors, we need to give some power. So unless until these two are working, this 1 will be maintained here, this 0 will be maintained here, right? Similarly, if I think if here is 1, now what is the complement of this one? 0. That means here I will get 0, here I will get 1. So this will be as it is unless until the power is delivered. So this is where these storage elements are started. So that is whenever there is cross coupled the inverters, so it can store some information, right? But here we need to give extra, that is there should be some external input whenever we want to store 0, whenever we want to store 1, so we have to give, right? But it is all started from here, right? So this is generally it is called bistable element. So what is this bistable element mean? So it can store two states, that is either 0 or 1, right? Even if you don't give any signal also here, if you connect series of inverters, you can easily generate 1 or 0, right? So that is possible using the inverters, right? So this is about this one. Now we'll see what are the differences between these latches and flip-flop. So many students have some doubts, right? So what is the difference between latch and flip-flop, right? If both are same or not different, we'll see. So both are different, that is for sure. How they are different, we'll see. So these latches are storage elements, but they will operate with signal levels, right? So these latches are operate with signal levels. That is, suppose if I'm having some clock like this, think like this. So this clock will have some levels. So this is called high level and this is called low level, right? If a storage element, right, not a latch, if a storage element is working or operating with these signal levels, whenever this high level comes, it is performing the operation. Whenever it is low level coming, so it is not performing any operation. So these type of devices or storage elements are called latches, right? Or we can say that is the latches are said to be level sensitive. Remember this point, latches are level sensitive. That means high level and low level, right? So high level comes, it may store. Low level comes, it may not operate also, right? So that is a latch, right? Now where we will use this type of latches, so generally we don't use in sequential circuit. So latches are used in asynchronous sequential circuit to store the information as well as the design the circuits, right? So that is the application of this latches. But these are the building blocks of the our flip-flops. So based on these latches only, we will know the theory of the flip-flops also. Now what is a flip-flop? So these are the storage elements that are controlled by or operated by clock transition. That is, so suppose same clock if I apply, clock transition means whenever there is a transition from 0 to 1, that is generally we say edge sensitive, right? So this is a positive edge, right? We will have positive edge clock, negative edge clock, right? This is 0 to 1. Some clocks will be there like this, same. Suppose this is falling edge, right? So this is falling from 1 to 0. So these are called positive edge clock, and these are called negative edge clock. So these storage elements or flip-flops generally are edge sensitive. So flip-flops are edge sensitive. So this is the main difference between flip-flop and latch. So latch is a level sensitive device and flip-flop is a edge sensitive device. So this is also level sensitive device. So this is the main difference between latch and flip-flop. And latches are used in asynchronous sequential circuit to store the information and for the design also. And these flip-flops where we use in synchronous sequential circuit to store the binary information, right? So now we'll see what are the different types of latches and what are the operations and how to design. Now we will discuss the first latch, that is SR latch, or we can say set reset latch. That is, it contains two states, that is either one state or zero state. That is, set means 1, reset means 0, right? Now we know the two cross coupled or two back-to-back inverters can store the binary information, right? But those inverter can be designed by using universal gates, that is either NOR gate or NAND gate. So we will have two different latches, that is using NOR gate, using NAND gates also. So we may get question from this using NOR gates latch or using NAND gates latch also, right? Now first we will discuss this SR latch using NOR gates, then we will discuss SR latch using NAND gates. Now when I connect to cross coupled NOR gates, something like this. This two NOR gates, and this output is coming back to the here, and it is becoming an input. These are the two external input. So we have to give, suppose if I want to store the information 1, so I have to give externally. So that's why these two inputs are there, and this is back connected here. So whenever you are using NOR gates, so the first input is R, the second one is S. So for R, the output will be Q, and for S, the output will be Q bar. So two inputs, two output. So generally this Q1 Q bar should be always complement to each other. That is very important point we need to remember. That is the reason also why these notations are implemented like this: Q1 Q bar. If Q equal to 0, what is the Q bar means? It should be 1, right? So that is a very important point we need to remember. So the outputs are complemented to each other. So this is a reset and this is set. It has two useful states, that is, so whenever Q equal to 0, right? So we can say it is in reset state. Whenever Q is equal to 1, so it will be in set state, depending on the input combinations. So how to make this functional table is, so I'm having two inputs. So how many combinations I can make? 4 combinations. So for 4 combinations, I'll get 4 different outputs. So that we will see one by one. Now we will see operation wise. So case 1, that is S is equal to 0, R is equal to 0. So when I apply this R is equal to 0 and S is equal to 0, so I cannot make comment on the Q value because I don't know the other input of the NOR gate. unless until I know the other input, I cannot make any comment on the NOR gate output. Yes or no? So that is the reason when we apply S is equal to 0, R is equal to 0. So we have to assume what is the present state. Then only I can get the next state. So assume, so present state Q equal to 0. So this is the assumption, because I cannot comment on when S and R equal to 0. So when Q equal to 0, so this is where it is going to this NOR gate, the bottom NOR gate. So S is equal to 0 and this Q equal to 0. So 0 plus 0, 0, but this is a NOR gate. What is a NOR gate operation? 0 plus 0 bar, A plus B whole bar. So what is that? I will get Q bar is equal to 1. And this Q bar is going back here. So what is this? 1 plus 0 bar. So 1 bar means I will get 0. So whatever we assume, we are getting the same, right? So present state and next state are same when S is equal to 0, R is equal to 0. So that is the case 1. Now in second case, suppose if I assume, this is the first case. If in second case, if I assume Q equal to 1, Q equal to 1. So then what will happen? So Q equal to 1. So this is coming back here, right? Then again 1 plus 0 means what? 1 bar. What I will get? 0. So this is coming back here and like this. So 0 plus 0, 0. 0 bar means 1. So whatever we assume, we are getting same. So present state and the next state will be same when we give S is equal to 0, R is equal to 0. So how can I make? When S is equal to 0, R is equal to 0. So we can say this is next state. So what is the next state? Whatever we assume the previous state, that is the one. So I can comment like this. So it is depends on the, or it is simply previous state, or we can say no change. So no change means there is no change in the previous, whatever the previous state is just follows. So that is the first case. That is when S is equal to 0, R is equal to 0. There is no change in the state. Whatever the state available, that will be stay as it is. Next we will see second condition. When S is equal to 0, R is equal to 1. Now when S is equal to 0 here and R is equal to 1. The moment one of the input of NOR gate is 1, I can make comment on the output. So 1 plus anything, 1 only. So 1 bar means what I will get? 0. So 0 is coming back here and it making 0 plus 0 whole bar. So 0 bar means 1. So what is this meaning? When S is equal to 0, we are getting Q equal to 0. Or we can say when R is equal to 1, we are getting Q equal to 0. What is this meaning? So reset value is high. So when reset is high, the output is it is becoming 0. And that means output is reset, right? Reset means it is like a 0. That is clear, right? So when reset input pin is high, then Q will be in reset state, or we can say 0 state. Next, the third case, when S is equal to 1, R is equal to 0. So when S is equal to 1, so no need of any other input. So directly 1 plus anything 1 bar means I will get 0. So 0 is coming here, R is equal to 0. So 0 plus bar, so I will get 1. So when S is equal to 1, this SR latch is storing the information as 1, or it is in set state. So this is the third case. Now fourth case, S is equal to 1, R is equal to 1. If both are equal to 1, so 1 plus anything 1, 1 bar means 0. And this is also 1 bar. 1 plus anything 1 bar means 0. But I told you in the beginning, the outputs should be complement to each other. So this, or we can say undefined state. This is called undefined state or metastables. That is, we cannot comment, right? So it should be in either 0 1 or 1 0, etc. But it should not be like same. So that means this input should not be applied, or this condition, input condition, should be forbidden. So it is unwanted state. So this state we can say forbidden state also. So the different names we can use: indeterminate state, undefined state, or forbidden state, right? So this condition should not happen in SR latch, right? Now we will form the functional table. So in functional table, whenever 0 0 is happening, what is the next state? So generally remember, whenever you are talking about the latch or flip flop, always we will talk about the present state and the next state. So depending on the input, so what is the next state? So whenever we give 0 0, so it will follow the previous state, or we can say simply no change, right? So this is the first condition. Now whenever we give s is equal to 0, r is equal to 1, so reset value is high, so q will become 0, that is q is becoming reset, or it is in reset state. And what is the opposite? 0 1. Next, when I give s is equal to 1, so we have to make output set, that means 1, then this is become 0. So 1 1, so this is called forbidden state, or we can say undefined state. So you whatever the name you want, forbidden state or undefined state. Now what is the graphic symbol, or generally we use symbol is, so a black rectangular box, so s and r the inputs and q and q bar as outputs, right? So this is about the SR latch using NOR gates. Now we will see SR latch using NAND gates. Now we will discuss about the SR latch using NAND gates. So this is the logic diagram of this SR latch using NAND gate. Now in this SR latch, the opposite of S is output Q and opposite of R is Q bar. So whereas in using NOR gates, so opposite of R is Q, opposite of S is Q bar, right? So there is a small difference between this and that. Just remember that point. Then we'll see the operation. Then we will comment on why we need to take R opposite of Q bar, etc. Now, whenever the cases will be same, to two inputs means we'll get 4 combinations of S is equal to 0, R is equal to 0. So the moment S is equal to 0, and we are using the NAND gate. Yes or no? So NAND gate input is 1, input is 0 means we can comment on the output. So the moment 0, so 0 into anything 0, so 0 bar means 1. So Q is equal to 1, and here also 0, so Q bar is equal to 1. So is it possible? So always these two should be in complement to each other. So again, what is the state? This is forbidden state, or we cannot allow these input combinations. So these input combinations should be forbidden. That's why we can say forbidden state or undefined state, right? Now in case 2, when S is equal to 0, R is equal to 1. So what happens? So NAND gate, so this is S is equal to 0 and this is Q, R, this is Q bar. What is R is equal to 1. So the moment S is equal to 0, the Q will become directly 1, because 0 into anything 0, so 0 bar means 1. So the Q is coming here, so 1 into 1, 1 bar means 0. Now see, complement to each other. See here, when S is equal to 0, we are getting Q is equal to 1, right? It is a complement of the what we got in the SR latch. So when S is equal to 0, in that case we got Q equal to 0, but here it is opposite, right? That we need to remember. Next, when S is equal to 1 and R is equal to 0, what will happen? We will see. This is S is equal to 1. So the moment S is equal to 1, or any one input of the NAND gate is 1, so we cannot comment. So we need another input, right? So to get another input, so there is a R is equal to 0. So the moment R is equal to 0, what is the Q bar will become directly 1, because 0 into anything 0. So 0 bar means 1 Q. So 1 means it is coming here. So 1 into 1, 1 bar means 0. Now it is opposite to each other, so it is valid. The moment R is equal to 0, what we are getting? Q equal to 0. Or we can say, yes, for S is equal to 1, we are getting Q equal to 0. So it is again opposite of the what we got in the SR latch using NOR gate. Next, final one, S is equal to 1, R is equal to 1. So this is the circuit diagram. So here S is equal to 1, R is equal to 1. So can I comment on this Q1 Q bar? I cannot, because we have to know the other input to comment on the output of the NAND gate. So what we will assume? So the first case, I will assume Q equal to 0. So the moment Q equal to 0, it comes here. So 0 into anything 0. So 0 bar means 1. So 1 is coming here. 1 into 1, 1 bar means 0. So whatever I assumed, I am getting same. Yes or no? In second case, if I assume Q equal to 1, so 1 is coming here again. So 1 into 1, 1. 1 bar means I will get 0. So 0 is coming here. 0 into anything 0. So 0 bar means I will get 1. So whatever we are assuming, we are getting same. So how can I comment on this one? So it is a no change in the state. So whatever the previous state, we are getting the same state as a next state also, right? Now if I see the functional table, if I draw, what I will get, see. So functional table, so whenever 0 0, this is called forbidden state. It should not be happen. So forbidden state. So whenever 0 1, so when s is equal to 0, we will get opposite in this NAND gate. So I will get 1 and this will become 0. So when s is equal to 1, I will get 0, here 1. So 1 1, so no change in this state. So no change, or we can say previous state also, right? Now if we compare this function table and the previous one, that is using NOR gate, for 0 0 we are getting no change here, and here for 0 0 we are getting forbidden state, and 1 1 we are getting no change. That is just opposite case. So if I make this S bar and R bar, I will get 1 1. So I will get no change. Similarly, all possible, you will see the complement of this functional table. So that is the reason this is SR latch, we can say, and this one is called S bar R bar latch. The symbol we can use is, for S, to get S bar, we have to make a bubble in front of the S and R. So this is the graphic symbol for SR latch using NAND gate. Whenever you see the bubble and nothing is there, it is simply SR latch using NAND gates. Now one more conclusion we have to draw here is, suppose if I give 1 1 in this SR latch using NAND gate, the output does not change. So whatever the state, it will be indefinitely, it will be in that state only, unless until we provide some extra from external input. So if I apply 0 1 only, then only the state will change. Suppose, think like this. First case 1, first I apply S is equal to 1, R is equal to 0. What is the corresponding outputs? So S is equal to 1 means I will get 0, this is 1, right? Now it is some, previously some state was there, now it is changed to 0 1. Now next case, if I apply S is equal to 1, R is equal to 1. So whatever the previous state, this will be there only. Now if you don't give any input after this 0 1 will be in that state only indefinitely, right? Unless until you give further S is equal to 0 or R is equal to 1, then only the state will change, right? So that is this how it is storing the information, 1 bit of information. Remember, always we will consider this Q is storing the information, right? So that is about the SR latch using NAND gate and NOR. Now we will see the SR latch with some control input, right? First, why this control input is necessary? Now if I see this SR latch using NAND gate or NOR gate, the moment inputs are changing, outputs will change, right? If it is 0 1, we may get 1 0. If it is a 1 0, we may get 0 1, and etc., right? The moments inputs are changing without our concern also, the output may change, right? That should not happen. Even inputs are changes, output should be remain same, right? Unless until we give the control input, right? Whenever we switch on the circuit, it should operate. Whenever the switch whenever we switch off the circuit, it should not operate. But it is looking like that only. So it will operate unless until the power is on, right? So that's why we need this control input. So here, why we are using, this is a NOR gates, but we are using AND gates as a control mechanism. How? Now if I see this AND gate, if I give one of the input is 1, so it will activate the operation. That is, if A equal to 0, I will get 0. If A is equal to 1, I will get 1. Yes or no? For AND gate, it will activate the operation when one of the input is 1. So that is the reason we are using the AND gate here. So what is the opposite of Q in a NOR gate? R. Opposite of Q bar? S. Now we'll see the operation. Now when any EN, so what is this EN is called? Enable input, right? So this is called enable input. That means it will enable the operation or enable the circuit or disable the circuit. So whenever the enable pin is equal to 0, so what will happen? So 0 is coming here and 0 is coming here, so it will not be activate, right? So we'll get what here? 0 0, right? Now whenever we give 0 0 for SR latch, what we will get? Just check in the previous case. So this is SR latch using NOR gate. So when I give 0 0, what is the next state? It is following the previous state. So Q and Q bar will remains in previous state, right? That means when we switch off the circuit, or that is a meaning, right? So when we switch off the circuit, it will be remain in the previous state. But don't conclude like that. So we have to switch on the power. So it is example I'm taking. When En is equal to 0, even the switch is on, it will be in the previous state only, right? Next, so when in that enable pin is equal to 1, now what you will get here? R and here S. So whatever the performance, it will be same as this truth table or function table. So whenever enable pin is equal to 1, it will follow the same operation. So when enable pin is equal to 1, what I will get? S and R and Q bar. So for 0 0, same you will get no change in the, or it will remain in previous state. When S is equal to 0, R is equal to 1, so set R reset is high, so output will be reset. So if it is 0 means it will be 1. If it is 1 0, so set 1, so output will be set and Q bar will be 0. 1 1, it is not possible, so I can say forbidden state, right? Now see, now whenever we want, we will enable this pin, then we will get the operation, or we will save some information. Whenever nothing is so when enable is 0, so it will disable the circuit, or we can say it will be in the previous state, right? That is very simple using the control input. Now what is the symbol? So I will draw the symbol here only. The symbol will be like this. So enable pin, this is En and this is S and this is R, Q and Q bar. This is a graphic symbol for SR latch using control input or enable input, right? So next we will discuss this SR latch using NAND gates with the control input, enable, or we can say enable input. So in this we will have only NAND gates. In the previous case, here NOR gates, here AND gate. So there is a reason why we need to use NAND gates here. But anyway, first we will discuss the opposite of Q is S, opposite of Q bar is R. Now why these are NAND gates? Now if I see the functional table of this S bar R bar latch using NAND gates, whenever we give 0 0, it will be in provident state. Whenever we give 1 1, it is in no change. That means it will retain the previous state. Now, so what is the condition we require when enable is equal to 0? That means the switch, the circuit is in disabled mode. So whenever it is in disabled mode, the output should not change. Yes or no? So who will make this like that? So when enable equal to 0, if I use NAND gate here, so 0 into anything 0, so 0 bar means 1. So here I will get 1, here I will get 1. So this is looking like a NAND gate, I mean SR latch using NAND gate. So if I give 1 1, I will get what? No change in the state. So for enable pin equal to 0, Q and Q bar in this latch will be remain in the previous state. So that is the reason why we are using the NAND gates in front of these two NAND gates, or to the enable pin and SR. Now when enable is equal to 1, what will happen? We will see. So when enable is equal to 1, what I will get? 1 into S complement. So I will get here S bar and R bar. But what we need, actually we need S and R, but we are getting S bar and R. Now the functional table will change compared to SR latch using NAND gate, because we are getting S bar R bar. How it is changing? If S is equal to 0, R is equal to 0. So what will happen? S bar is equal to 1, R bar is equal to 1. So when S bar is equal to 1, R bar is equal to 1, this is a NAND gate. So I am giving 1 1. So what I will get, the Q and Q bar is no change. That is the first condition. When enable pin is equal to 1, when S is equal to 0, R is equal to 1, what I will get, S bar is equal to 1, R bar is equal to 0. What we will get, Q1 Q bar. So S bar I have directly applied here 1 and 0. So the moment this is 0, what I will get, 1. So this is coming here 1 into 1, I will get 0. See here, whatever we are giving, S is equal to 0, we are getting Q is also 0. R is equal to 1, we are getting Q bar is equal to 1. Or we can say when reset is high, the output is getting 0 or it is reset. It is in reset state. Next we will see third one, that is S is equal to 1, R is equal to 0. So what will happen, S bar is equal to 0, R bar is equal to 1. So I will apply in this diagram only. So S bar 0, R 1. The moment it is 0, what I will get, 1. This is coming back 1 1. So I will get 0. So what is the output? Q is becoming 1, Q bar is becoming 0. See, S is equal to 1. So the set is high. So we are getting the output is in set state. So Q bar is what? 0, not 1. Okay. So remember this one. If this is 1, I'll get 0 here. So 0 0 0 1 1 0. So what is the last case? S is equal to 1, R is equal to 1. So what is this? It will become S bar equal to 0, R bar is equal to 0. So if I apply this in this one, this is 0, this is 0. So no need of another input, right? So what I will get, 1 1. So what is this? Forbidden state. Forbidden state. Now see, what is this function table? If I draw the functional table of this latch, this is Q and Q bar. So what I will get? So 0 0. What we are getting? No change. When enable is equal to 1. 1 1 1. So 0 1 1 0 1 1. So 1 1, forbidden state. Forbidden state. So when S is equal to 0, R is equal to 1, what we are getting? See, 0 and 1. Q equal to 0, Q bar is equal to 1. So 0 and 1. Next one, 1 0. So 1 0 means we are getting 1 0 only. Now this is the same truth table of this SR latch using NOR gate. Yes or no? So that is the reason when we use this enable pin, SR latch using NOR gate with control input, SR latch using NAND gates using control input, you will get the same truth table. So that is the useful of this enable pin. So any circuit, if it is a NOR gate or a NAND gate, so you will get the same functional table. But in using NOR gate, we have to use AND gates here for the control input, right? Now for this one, you can use same the logic symbol or a symbol, that is, this is enable pin and this is S and this is R, this is Q and Q bar. So there is no S bar R bar latch, because this functional table and this SR latch using NOR gate with enable, you'll get the same functional table. So that is the reason we can use the same graphic symbol, SR and enable Q1 Q bar, right? So you have to remember the 4 truth tables. Using control input, either NOR gates or NAND gates, you will get the same truth table. Yes or no? And using NAND gate only, no control input, you will get the just opposite of the NOR gate functional table, right? So just one more time you do on your own, then it will be very simple. Next we will discuss the D-Latch. So other names of D-Latch are transparent latch or delay latch. So why the name comes is that will be justified in 3 minutes. But what was the problem in SR latch? So we are getting when S is equal to 1, R is equal to 1. When S is equal to 1, R is equal to 1. So we are getting Q and Q bar both are equal to either 0 0 or 1 1. So which is not possible. Yes or no? So this is, we can say, undefined state, or we can say forbidden state. Now how to eliminate that state is, whenever S is equal to 1, R is equal to 1, we are getting this undefined state. Now if we are using some mechanism and we are never making this S is equal to 1, R is equal to 1, then we can easily remove that undefined state. How? So take this S and give it to one inverter and give it to this R. Now see, when S is equal to 1, R will become 0. When S is equal to 0, R will become 1. So these both will never be equal to 1 at a time. Then we can easily eliminate that undefined state or forbidden state. Here only one input is enough to represent this one. So what we do is, so this S are simply replaced by D here. Now see, this is D is going here and D bar is going here. So here I can make S is equal to D and R is equal to D bar. So that is SR latch is converting into D latch, something like this. So this is a D latch. Now we will see the operation. So based on the operation, we will justify how the transparent latch or delay latch. Now think that the operation when D is equal to 0. So when D is equal to 0, what is the operation? So when D equal to 0, this is 0 and this is 1. So 0 into anything 0, so I will get 1 here. What is this? I will get, okay, this is an enable pin. So enable pin is always 1. So 1 into 1, I will get 0. So this is 0 means Q bar will be 1 and this is 1 1 means I will get 0. So when D is equal to 0 and enable pin is equal to high, what is the Q? It is 0 and Q bar anyway 1. Now see, whatever we have given the input, so that is just passing to the output. Yes or no? So after this combination circuit or this logic gate, so they will take some delay, right? So to convert or to pass this information to the output. So that's why it is called delay latch, because the same output we are getting after some delay. So that's why it is delay latch. Now second condition, if D is equal to 1 and enable pin is equal to 1, so what I will get? So this is 1, opposite means 0. So 0 into anything, I will get 1. So enable 1 1, I will get what? 0. So 0 into anything 0. So what is the output? Q is equal to 1. This one is, so 1 is coming here, 1 1. So I will get what? 0. So D is equal to 1. What is the Q? Q is equal to 1. So whatever we are giving, we are taking to the output. So that's why it is called transparent. So whatever the input, so we are getting the same at the output. So it is looking like a transparent. So that's called transparent latch. So it's just passing the information from input to the output. That's why either delay latch or transparent latch. Right? Now if I draw the functional table, then so what is the functional table? Function table. If enable is equal to, so enable pin, that is D. When enable equal to 0, so whatever the input, the D input, it does not change the output. So it will be in previous state only. The next state will be previous state. When enable is equal to 1, when we give D equal to 0, I will get 0. When D is equal to, this is enable is 1, when D is equal to 1, I will get 1 only. So Q bar means opposite anyway. So this is 1, this is 0. So when 0, D, output is also 0. When D is equal to 1, output is also 1. When enable pin is equal to 1. Now how to represent? I mean, using a logic symbol is, this is D and this is enable pin, Q and Q bar. Right? So this is the delay latch or transparent latch. Now we will discuss the last concept in this latches, that is D-Latch with preset and clear inputs. So we can design the SR latch with preset and clear also. So same operation it will be. So what is this preset and clear is? So presetting means, so we can set the output as Q is equal to 1 even without giving some inputs and enable pin also, right? Or we can clear the outputs also. So when clear is equal to 0, the Q will become 0 directly and the Q bar will become 1. So that is why these bubbles are indicating is, it is a active low input. 0, I mean a bubble means active low input. We can, without bubble means active high input. That means when PR is equal to 1, it will become, the output will become 1. When CL is equal to 1, the output will become 0. That is it is clearing the output, right? Now this preset and clear will not depend on the inputs. So that is the reason why these are called asynchronous inputs, right? This preset and clear inputs are called asynchronous inputs, because these inputs will not depend on the either enable pin or input pin, that is D. So that's why it is called asynchronous input. So what is this operation is, when preset is equal to 0, because it is active low, the Q will become 1, that is it is in set state. When CL is equal to 0, so it will be in reset state. Now how the logic diagram is, so in this first NAND gates, so I will give one extra pin, that is PR bar and CL bar. Now see, the moment PR is equal to 0, that our PR bar is equal to 0, right? So PR bar is equal to 0. So what will happen? So 0 into anything, I will get 1 only. Yes or no? So this is 1. So depending on this, I should get opposite here. So the moment preset bar is equal to 0, it will not see either enable pin or D input. The moment it sees preset equal to 0, the output Q will become directly 1. In the second case, okay, this is the first case. If CL bar is equal to 0, this is the second case. So Q bar directly what it will become? CL bar equal to 0 means what? Q bar is equal to 1 and Q will become 0. So CL bar means Q should be 0 and PR bar equal to 0, Q will be 1. So it is in set state. When CL bar equal to 0, it is in reset state. Similarly, we can design same SR flip-flop using preset and clear. Right? What we need to do here, S and R without NAND, NOT gate. Here you will get preset and clear bar. Right? So that is about this preset and clear inputs. These are the inputs are called asynchronous inputs, because the operation of these inputs will not depend on the inputs of this latch, either D input or enable input. Right? In the next lecture, we will start the flip-flops, that is SR flip-flop, D flip-flop and so on. Right?